Hi, my name is Holden Rogers, and I am a junior from Raleigh, North Carolina, majoring in chemistry and mathematics. This past semester, I had the pleasure of mentoring for Dr. Crimmins in Chem 261, and I look forward to mentoring in 262 during the spring semester. This past semester, it was my first time mentoring, and I think it's fair to say I had a really fun time doing it. One of my favorite things is seeing that aha moment going across the student's face once they finally understand a concept, and being able to be a part of that and getting the message and material across to them in a coherent way is something that I really enjoyed, and I really look forward to doing once again next semester. Okay, so let's look at the problem that we have here, and it asks us to draw the mechanism of the following reaction. And this type of reaction is what we call an EAS reaction, and it's something that we'll see quite often at the beginning of 262. And the EAS stands for electrophilic aromatic substitution. And in these types of reactions, there's 5 main ones. In this case, we're going to be doing a nitration based on the reagents that we have here. And in these types of reactions, we're going to take an electrophile and we're going to substitute it for a hydrogen on the aromatic ring. So in order to get started, what we need to do is what we call the generation of the super electrophile. And the super electrophile is just an easy way to say that we're going to create a reagent that is an electron acceptor, and it'll easily accept the electrons from this benzene ring. So let's go to the bottom here and generate our super electrophile. And what we're going to do is we're going to take this OH group and we're going to try to make it a better leaving group in order to create what we call a nitronium ion. And the nitronium ion is a really strong electrophile, which means it's easily accepting electrons. And to do this, what we're going to do is we're going to take the lone pair from this oxygen and we're going to go over to our sulfuric acid catalyst and we're going to take one of the hydrogens away. And what this does is allows us to make a better leaving group, such as water, and we're going to knock it off. So to knock it off, we're going to take these electrons, we're going to drop them down, and then since nitrogen can only have 4 bonds, we're going to kick off the water, and that's going to leave us what we want, which is the nitronium ion, which has a positive charge. So let's go up to the top here and write in our nitronium ion. And so before we go through the mechanisms, there's a few things that we need to discuss that you already know, and it has to deal with the benzene ring itself and what's attached to it. So this substituent right here is a CF3 group, and what we know is that the fluorines are really electronegative. And this electronegativity of the fluorine is going to impact how our nitronium ion is going to add to the benzene ring. And so what we know is that the CF3 group is what we call a deactivating substituent, and it's a substituent that decreases the reactivity of an aromatic ring. And all this means is that it's electron withdrawing, and these fluorines, since they're so electronegative, they're going to take these electrons out of the benzene ring, not necessarily out of, but they're going to pull the electrons away from the benzene ring and make it less likely to do an electrophilic attack. Now it still will, and that's how we're going to get our product over here, but it's going to change where this nitronium ion can add. So this CF3 group is going to be what we call a meta-director. And so what we know from this from class is that meta-directors are going to add to the second carbon over from where the substituent is. So it's going to add here, as we can see in our product. So now that we know where it's going to add and how it's going to add, let's do the mechanism. So we're going to take these electrons from the benzene ring and we're going to attack the positive charge from our super electrophile that we created below. And we're going to push these electrons back onto the oxygen. And so let's draw the result that we have here. And what this is going to do is it's going to leave a positive charge on the benzene ring. Now, from when we learned in class, aromaticity is something that's really stable. So this is what is going to be called the rate determining step, which means on a reaction diagram, this step is going to be the most endergonic, and it's going to take the most amount of energy to do. Now this reaction in general will be exergonic, but this first step is going to be the slowest, and it's going to take the most energy. So once we have, I forgot our substituent over here. So once we have this, what we're going to do is we're going to need a base to take away this hydrogen and remake the double bond within the benzene ring to make it more stable. So the base that we have in solution right now actually comes from our catalyst, and it comes from our generation of the superelectrophile, and it's going to be the sulfuric acid anion. Take off that hydrogen because it's no longer there. And so we're going to take these electrons from the oxygen on the sulfuric acid anion, and we're going to take the hydrogen off from the carbon where we attach the nitronium ion, and these electrons from the hydrogen are going to go back into place on the ring, and it's going to recreate the benzene ring, and we're going to get our product over here. So let's do a little recap here. So for this electrophilic aromatic substitution reaction, we did a nitration, and our goal was adding an NO2 onto the benzene ring. And the first step that we had to do was this, what we call the generation of the superelectrophile. And we did this by taking our nitric acid and our sulfuric acid and generating the nitronium ion. And we did this by adding a hydrogen to this oxygen, which allowed it to be a better leaving group, as water is a better leaving group than the OH group for it. And then we took this nitronium ion and we added to the benzene ring. And since this benzene ring had a CF3 group, which we know is strongly deactivating, it was going to undergo a meta addition. And since this CF3 group is a meta director. And so once we added the nitronium ion, we took the sulfuric acid anion that we created in our generation of the superelectrophile, and we took the hydrogen from the benzene ring and we recreated the double bond in order to recreate its aromaticity. And this is something that's really stable, which allows this reaction in general to be an exergonic reaction. Now notice that we had the regeneration, I should write that in, we had the regeneration of our catalyst, which always occurs in these types of reactions. And so there you go, there's a nitration reaction, and hopefully this helped.